A Carnegie Institution for Science audio press release for May 20th, 2015. Strong UV pulse reveals supernova's origin story. Type 1a supernovas are violent stellar explosions that shine as some of the brightest objects in the universe. But there are still many mysteries surrounding their origin, what kind of star system they originate in, and how the explosions began. New work from the intermediate Palomar Transient Factory team of astronomers, including Carnegie's Mansi Kasliwal, provides strong evidence pointing toward one origin theory called the single degenerate channel. This work is published May 21st by the journal Nature. Type 1a supernovas are commonly theorized to be the thermonuclear explosions of a white dwarf star that's part of a binary system, two stars that are physically close and orbit around a common center of mass. But how this white dwarf goes from binary star system to Type 1a supernova is a matter of debate. The single degenerate channel theory hypothesizes that the white dwarf accretes matter from its companion star, and the resulting increase in its central pressure and temperature reaches a tipping point and ignites a thermonuclear explosion. In contrast, the double degenerate theory proposes that the orbit between two white dwarf stars shrinks until the lighter star's path is disrupted and it moves close enough for some of its matter to be absorbed into the primary white dwarf and initiate an explosion. Last May, the Palomar Transient Factory team observed an explosion in the vicinity of a galaxy called IC 831, where no such activity had been seen previously, even the very night before. They called it IPTF 14ATG. Follow-up observations confirmed that this was indeed a Type 1a supernova, one which ignited between May 2nd and May 3rd. Looking at the event from Swift Space Telescope observation records, the team detected bright ultraviolet emissions from the new supernova. Caltech graduate student Yi Chao, lead author of the paper, says, "I was examining the first Swift images when suddenly I saw a bright spot at the location of the supernova in the ultraviolet. I jumped up because I knew it was the signature that I'd been hoping for." Because ultraviolet radiation is higher energy than visible light, it's particularly suited to observing very hot objects like supernovas. Such an early UV pulse within days of a supernova's explosion is unprecedented. This strong pulse of emission is consistent with theoretical expectations of collision between material being ejected from a supernova explosion and the companion star from which it has been accreting matter. Kasliwal says that this provides good evidence that at least some Type 1a supernovas arise from the single degenerate channel. Now we have to determine the fraction of Type 1a that are akin to IPTF 14ATG. They sought a better understanding of the newly discovered supernova, and particularly of the UV pulse, comparing it to known supernovas in the Type 1a family. Their spectroscopic findings with the Apache Point, Gemini, Palomar 200-inch, Nordic Optical Telescope, and Keck observatories indicate that IPTF 14ATG is a low-velocity Type 1a. The team thinks it's likely other low-velocity Type 1a supernovas also arose from the single degenerate channel. However, there are other higher-velocity 1a supernovas that likely originate from the double degenerate pathway, as other studies have indicated. The team's findings indicate that UV observations of young supernovas could hold the key to fully understanding the pre-explosion interaction between a supernova's white dwarf progenitor and its companion. This image is from a simulation in which a Type 1a supernova explodes, as shown in brown. The supernova material is ejected outward at a velocity of about 10,000 kilometers per second and slams into its companion star, as shown in light blue. The collision produces an ultraviolet pulse, which is emitted from the conical hole carved out by the companion star. The image is courtesy of Dan Kaysen of the University of California, Berkeley. With the independence for nimble pursuit, Carnegie scientists tackle some of the most profound challenges in modern science, fundamentally changing what's possible for us, our planet, and our universe.